All right, this is a demonstration for how to get set up with Tensor Foundation's smart contract repos. This will cover setting up, building, and running tests, as well as generating the clients, which should be enough to learn how the program functions. You can use the tests to jumpstart off of for your auditing approaches. You'll need some prerequisites installed. You'll need Rust 1.78. You'll need Anchor 0.29. You'll need Solana 1.17. We use 1.17.23 usually. You'll need the PNPM package manager, and Node version 18, 20, or 22 should work. All these smart contract repos have a similar setup based on the Solana create program template. This repo here. This is the fastest way to get started with creating a Solana program, in my opinion, and it uses the new Web3.js 2.0. So this is the AMM program, but again, all of these programs will have a similar setup. They all have a clients directory. This contains auto-generated JavaScript and Rust clients. The JavaScript one, you'll see all the generated stuff from the IDLs in this generated folder. The hooked is where we add additional helpers, utilities, accounts, that sort of thing. And then there's a test directory. We do most of our integration tests in JavaScript. And so this is a good place to look for examples for how to call the various instructions of the program, as well as to see the sorts of things we're already testing on the program. And again, this is in the new Web3.js 2.0. So if you're not familiar with it, you might need to go look at the Solana docs for it. The Rust client also has a generated section, which is generated from the IDL, and it may have a hooked section with additions to the client. And then it may or may not have tests. Typically, we do write a few Rust tests, but most of our tests are written with a JavaScript client, so this may not be present in all of the repos. Next, there may be an examples folder. If so, this will just contain some TypeScript examples for how to call various instructions of the program. Another good place to look for when you're testing the program. Then the program directory has the actual smart contract code itself. These are all Anchor programs, so we'll follow a very familiar Anchor setup. Finally, there's a scripts directory. This contains various scripts for downloading programs and accounts to run on the local validator, generating the IDL, generating the clients, starting and stopping and running the local validator, and running tests. So we'll go ahead and clone this repo. So all the scripts to set up and run this repo are here under the package.json. So we use pnpm to run these, and there are some basic dependencies that need to be installed first. So the first thing to do is run pnpm install. Next, we're going to run pnpm programs build. What this does is it will grab all of the needed programs and accounts from a Solana cluster in order to run these on the local validator. So these are various external programs we need for our tests. Maybe we're creating different NFTs from NFT standards, and it downloads them so we can run them on the local validator. Then it goes ahead and builds the actual program itself. And these are going to all end up in the target deploy directory. You can see the external programs. When it finishes building this program, it'll be here as well. So you can choose which cluster to pull them from, DevNet or mainnet. By default, it's DevNet. And then additionally, you can do programs build artifacts. What this will do is, instead of, for any Tensor Foundation programs, instead of downloading them from the cluster. It will actually pull them from the latest GitHub build artifact in Tensor's repos. So if you wanted to test against some bug fix that we have put into the repos but haven't put onto chain yet, you could use this. This will not affect where it pulls the external programs from, though. All right, so now we've built a program and pulled down the accounts and external programs we need for the validator. We're going to then run pm generate. What this does is it generates the IDLs and the clients. You can do these individually with these individual commands, or you can do them together with generate. Now, one thing here is that the first thing it does is it's going to install the specific Anchor binary that it needs to run. So it's going to try to put the Anchor binary in a .bin directory here. But the problem is version 0.29 has some Solana dependency build issues, so I think it's going to fail here. So we might need to do a little workaround where we copy the binary from elsewhere and put it specifically in this folder. I do have Anchor 29 installed via the normal methods using the Anchor version management CLI AVM. So if this fails, we'll go ahead and just copy that binary manually, but we'll see if it works. All right, looks like it did work. That's excellent. So we now have our Anchor binary and we're good to go. We've generated our clients. Now, there shouldn't be any changes here. We do commit the IDL and the clients, so there shouldn't be any changes since the last time we committed to the repo. But if you were to change something in the program because you wanted to test some potential issue and you wanted the clients to update, you could run this generate. It would regenerate the IDL, regenerate the clients, and now you could use those new clients as needed. Finally, I'm going to show you how to run the tests. Might be useful if you're modifying tests to try out different things. You do pm clients JS test. This will install all the dependencies needed for the JavaScript client. It will spin up the local validator. It will build the JavaScript client, and then it will run the JavaScript tests. So while this is running, we can also do the same thing here for Rust. The difference here is that the Rust tests are actually using the Solana Banks client. So rather than spinning up this local validator using the Solana test validator, it uses the Solana Banks client. But otherwise, it will build the Rust client and run the Rust tests. So here, all of our JavaScript tests are running. And when this is done, it will run Rust tests. So that's basically it. All of these repos will have a similar setup, and this should be enough to get you started. And then we'll have separate overviews of each program covering the details and operation of the program itself in separate videos. This is an overview of the Tensor Foundation Toolbox repo. Unlike the other repos covered in other videos, this is not a program. Rather, this is a collection of helper functions and utilities that are used across the various programs. So this toolbox has two main crates. It has a toolbox crate, which has a bunch of shared functions, and it has a fork of Vipers that has been updated to use Anchor 0.29. So here's the original Vipers crate that is not maintained any longer. So Tensor has a fork that is updated to Anchor 29 and has some other minor modifications. So we'll take a quick look at the code. There's not a lot here. The way to evaluate this code is probably incidentally to the program. So when auditing the programs and you see a shared function, you can follow it and validate it's doing what it's expected to be doing. That's probably the most efficient way to do it, but you can see we have a common file, that's got various utility functions, particularly around transferring LAN ports, closing accounts, transferring creators' fees for paying out royalties, and things like that. And then it has some program IDs and pub keys to find. There's a CNFT specific file for transferring compressed NFTs. There is a token metadata file that has some assertions for decoding metadata and some utility functions for transferring. And then there's a smattering of other things, some validation for core assets, some validation for token 2022 assets, including WNS assets. And a few other things. One thing you might run across is we have some custom errors here that are thrown within these functions in this toolbox crate. So sometimes these will be errors you'll see rather than program-specific errors, depending on if the helper function is called. And in Anchor will add 6,000 to these error numbers, so you'll probably see 15,009, 15,005 instead of 9,000. The crate has various features. So you can enable these various features if you don't need them all to save on compile time. And that's basically it. Vipers contains a bunch of helpful macros and assertions for dealing with Anchor programs. Lets you unwrap optionals, throw errors, assert various things. And that's it for this repo. This video is an overview of the Tensor Foundation's Whitelist program, which is a way to manage collections of NFTs and other assets on-chain. Program's ID is TList. It's on both DevNet and mainnet, but the new V2 functionality may not be on mainnet yet by the time you're watching this video. The best place, I think, to start with this program is in state, as there are two main accounts that define this program, the whitelist and the mint proof, and we'll look at both of these. But a quick note is that you'll see distinctions between the original whitelist code and the new functionality, which is all suffixed with V2. You should focus your auditing efforts on V2, as the original functionality is deprecated and will eventually be removed. However, if you find any bugs in the original stuff, you should of course report it, but we will focus our overview on the V2 functionality, as that's what will be used going forward. So we'll start by looking at the whitelist account itself. This account defines the whitelist, specifies various things about it, its state, its authority, and the conditions that gatekeep what assets are in the collection. So the whitelist account is a PDA on the TList program derived from the string whitelist, namespace, and UUID. The namespace is a public key that must also sign when creating the whitelist. And the UUID is a 32-byte identifier chosen by the creator of the whitelist. Neither of these can be updated as they're tied specifically to the whitelist account. Version field is just used to differentiate if any additional changes are made to the program. Lets reallocation happen depending on the version type. Bump is where the PDA seed is stored. We discuss UUID. State just defines whether or not the whitelist is frozen or unfrozen. If it's frozen, it can't be edited, updated, The update authority is the authority that can control the whitelist. It is allowed to update the whitelist by changing the conditions, but it cannot freeze or unfreeze the whitelist, which is a separate control. The namespace is a way to group whitelists together in a permanent way without relying on the update authority, as the update authority itself can be changed. So for users who do not care about the namespace, they can generate a random private key, sign with it for creating the whitelist, and then throw it away. But users can also create a specific private key they use across multiple whitelists to group them together. Freeze authority is authority separate from update authority that is able to freeze and unfreeze whitelists. And finally, the conditions are what determine what items are part of the whitelist. So we'll look at conditions. Conditions are made up of a mode and a value. The mode is the type of condition it is, and the value is the pub key associated with that mode. So we only have 3 conditions supported currently. There's Merkle tree, verified on chain, and first verified creator. Merkle tree has a value of a 32-byte root hash of a Merkle tree. And so any item that's a valid member of this Merkle tree is a valid member of the whitelist. We will use the mint proof account to validate that an item is part of a Merkle tree, which we'll go over later. Verified on chain is just basically an NFT collection. There are different standards that specify collections in different ways, but for any particular standard, if it has a verified collection, this will point to that value, and any item that's part of that collection will be a valid part of this whitelist. First verified creator is similar, but for a verified creator in an asset or NFTs metadata. So the way that the whitelist gatekeeps conditions is you can stack conditions. You can have up to 24 different conditions specified by the conditions length, with the restriction that you can only have 1 Merkle root currently, but you can have as many collections or first verified creators as you want, up to 24. And these are ORed, so as soon as one of the conditions is true, an item is considered to be a valid part of that whitelist. These are some helper functions to validate conditions, to verify whitelists by taking in the different possible values and doing the validation. So let's look at creating a whitelist next. To create a whitelist, you optionally specify freeze authority and conditions. Although actually, yes, you optionally specify a freeze authority and a list of conditions. You have to sign with 3 different key pairs, which may seem excessive, but there's good reason for this. We have a separate payer so that a payer can pay to create for a bunch of whitelists for users. However, in many cases, update authority and payer may be the same. Update authority is the key pair that will be able to edit the whitelist going forward. Namespace, as we discussed above, is a unique identifier that can be used to group whitelists together. And then you have the whitelist account and system program. Fairly simple. Some explanation here. Because conditions is a vector that can be various sizes, we need to dynamically allocate the specific amount of space required. So we start with the whitelist v2 base size, which is defined here on the whitelist impl. And the base size is basically the discriminator size, so the anchor 8-byte discriminator, plus its anchor init macro space, which is all of these fields here except for the conditions. So it includes the 4 bytes of the vector length, which Borscht uses 4 bytes to represent a vector length, but does not include any of the conditions. So this would be a base whitelist with 0 conditions. And then we start with that, and then we add the number of conditions that the user has specified times the condition size. So this gets us the actual space the whitelist will need on chain, so that we don't have to allocate more than we need. And when we edit, we also reallocate smaller or larger. Other than that, it's a very simple, straightforward creation handler. It uses anchor constraints to tie together the whitelist seeds. It requires some signers, and then it sets values. And all whitelists start off as unfrozen. Now, the freeze authority is optional. So if it's not set by the user, it defaults to the default pub key, which we use so that we can have a constant 32 bytes for the freeze authority in the account state here. So basically this, you can think of this as like a nullable pub key, where if it's the default pub key, we consider it to be a null value, and any other pub key is something set to a specific freeze authority. This works because, of course, the default pub key is the Solana system program, and it's not going to be signing for any freezing or unfreezing of anything. So that's the create whitelist. Let's look at update whitelist. This one takes an option of conditions, where if you specify the option as none, it's treated as a no-op. We're not changing any conditions. If you pass in some conditions, it will replace the old conditions with the ones passed in. And then we have an operation type for the freeze authority, because there's basically 3 actions you can perform on it. The first is doing nothing, a no-op. The second is clearing. So you take the freeze authority from something and set it to the default pub key as a null value, or you can set it to some new value. We use this 3-state operation because a Rust option type could be ambiguous, because if you pass in none, it's unclear if you're trying to clear it or if you're trying to set it to, or if you're trying to no-op on it, basically. Then we have a payer, which is used to pay for reallocation of the whitelist. If it gets larger, or to receive the extra funding if the whitelist is reallocated to be smaller. We have to have an update authority to sign off on the update. And then if we're setting a new update authority, that also must be passed in as a signer to prevent accidentally assigning the update authority to some random account that isn't meant to have it. And then here we have some math here that basically what this does are conditions as ref, unwrap, or whitelist conditions.length. This just gets us either the passed in conditions, if there's some, or the length of the current conditions. We multiply that by the condition size and add it to the base, and this will be the amount of bytes to reallocate for the whitelist. If they don't pass in anything, this will be the same as what exists, so there won't be any reallocation. Otherwise, if it's smaller or larger, it will do the reallocates appropriately. Out of an abundance of caution, we're zero initializing the realloc, even though that's not really necessary in this case. We set the pair, we perform an has one check on the update authority. And then here we make sure it's not frozen before we update. We validate conditions, we set values. Then we have freeze whitelist and unfreeze whitelist, which are symmetrical and very simple. You check that the freeze authority is the one signing off. You validate that it's a valid whitelist, and then you can set the state. All right, then you can close a whitelist. Only the update authority can close the whitelist. They must be a signer. You cannot close a frozen whitelist. Must be update authority. And we're using Anchor's close macro, so this is pretty straightforward as well. Those are the whitelist instructions. Now let's take a look at mint proof. So this is a count specific to Merkle root conditions that lets us store these long Merkle proofs in an account specifically, so we don't have to pass all of that in on the validation for the whitelist itself. These are designed to be created on the fly when needed, so you can create them in the same transaction if you need. They are derived from the seeds, mint proof v2, the actual mint account, and the whitelist account, so they're tied specifically to a mint, which is representing either an NFT or an actual asset, as in an MPL core asset, and a specific whitelist. One unique aspect here is that when we create these, we record a creation slot, and we record the original account pair. And so this is that if you're closing within a 100 slot delay, the original account payer will receive the rent, and the original account payer is the only authority that is able to close the mint proof. But after 100 slots, they're fair game, and anybody can sign to close the mint proof, and in doing so will receive the rent of the mint proof account. This is to incentivize cleaning up old mint proofs so that they don't bloat account state. So you can init update mint proofs. This is basically an upsert, so that you don't have to know if your necessary mint proof exists or not. You can just call this upsert, and if it doesn't exist, it will create it, and if it does exist, it will update it. So this mint used to be checked as an actual SPL mint type, but it is no longer checked as an SPL mint type because we support also non-token based NFT standards such as MPL core, which is a single asset account and doesn't have a mint. So in that case, this is the actual asset address instead of the mint. So the mint proof is in it if needed. The payer pays for it. We do seeds derivation. We use the fixed size and go through and create the mint proof. Requires validating that the proof passed in is valid against the Merkle root in the whitelist, and that the mint proof is not too long. And then we set the creation slot, and we set the payer if it's not already set. So we use the same pattern here as we do on freeze authority, where it's just a 32-byte pub key. But if it's the default pub key, we know it was all zeros, so it was uninitialized, and then we go ahead and set it. This prevents us from overwriting the mint proof pair. You can close the mint proof account. As we talked about, there's this 100 slot delay before which only the original pair can close the mint proof and they receive the funds. And after which the signer is able to, any signer may call and close the account and receive the rent back to incentivize cleaning up state. So those are most of the functionality and state. We have a full Merkle proof. This is just the Anchor account set up so that it makes it into the IDL, I believe. And then we have the old versions, which are similar, but they're deprecated and will be going away soon, so we're not going to go over them in great detail. I think that's a good overview of this program. This is an overview of the Tensor Foundation Escrow program. This program ID is tswap, and so it's the former tswap program that had AMM pool functionality as well as listings for CNFT and MPL core assets, but all of the listing and pool functionality has been removed, and so now it is solely an escrow program. So it's a shared escrow account to handle pooled liquidity that can be used across multiple pools, multiple AMM pools, or multiple marketplace bids. So fairly simple program now. It has two state accounts, the margin account, which defines the shared escrow account. And a quick note here is anywhere in this program you see margin, you can mentally substitute as escrow or shared escrow. Due to backwards compatibility issues, we didn't rename it everywhere, but it's the same thing. So the margin account, this is just the account that stores the pooled liquidity that can be shared across multiple bids or pools. And it has an owner who is the authority that can withdraw or deposit funds to the account. It has a name and a number, which are owner specified to be able to differentiate different pools, and some extra account space in case we add new fields in the future. This pools attached field is deprecated. We are no longer tracking how many pools are attached because it's easy to get out of sync. And these shared escrow accounts can be used for more than just pools. They can be used in bids as well, so it doesn't make sense to just track pools. There's a tswap singleton PDA, which is part of a sort of deprecated way of doing cosigner control of accounts, which we don't really use anymore, but due to some backwards compatibility, it's still here. You don't have to worry too much about it. So there are various instructions. You can init a margin account. This does require passing in the tswap singleton PDA, but it's not, and using that as a seed, but it's not really used other than that. And an owner, which must be a signer. And it sets up the account. You can close an account you're no longer using. The owner must sign. And when the account is closed, any funds on it, the rent and any additional funds above the rent, go to the owner. You can deposit to a margin account. Which just does the transfer LAN ports for you. Of course, you could do this directly. Because sending SOL to any account is permissionless, but the deposit is nice to use because it makes for better indexing and logging. And then there's withdraw. So this the owner must sign in order to withdraw funds from the account. Again, very simple, very basic. Then there are two CPI specific commands. So withdraw margin account from TAMM. This allows a pool account originating from the TAMM program to withdraw funds so that a pool can fund itself from a shared escrow account when a NFT is bought, or sorry, when a when an NFT is sold into the pool, so effectively when an NFT bid is taken. And it requires that the pool account be a signer, which enforces that only this program can call this instruction, because PDAs can only be signed for by the originating program due to runtime enforcement and the nature of how PDAs are off-curve keys. So they have no private key. You have to pass in the owner just to make sure it's the correct margin account, and this ties the pool to the margin account. We check the pool's discriminator to double check that it is the correct account calling it. And we have a similar withdraw margin account from tcomp, which is for the marketplace program. But the same idea, you can have a bid state PDA be a signer in order to withdraw liquidity from a shared escrow account. And we also check the discriminator here. So those are all the instructions. This is a init update tswap creates the singleton PDA. This is called once. It's already been initialized, cannot be called again. But that's it. It's a pretty straightforward program, shared liquidity that can be used across multiple pools or bids. It has withdraw margin account, permission to an owner. It also has 2 CPI calls, which are permission to the TAMM program and the tcomp marketplace program, respectively. This is an overview of the Tensor Foundation fees repo. So this program is the TFEE program, and it's deployed to both DevNet and mainnet at this point. And it's exceedingly simple as a single instruction collect. And so the idea here is that formerly, the Tensor protocol used to take fees on singleton PDAs in each specific program that charged fees. So tswap had its own singleton fee PDA, and tcomp had its own, etc. The issue with this is that using a single mutable account across the whole program write locks and forces any call to be serial. Because of Solana's runtime, that enforces that mutable accounts can only be used one at a time to prevent race conditions. So this is not an efficient way to take fees. It hurts the performance of programs, causes a lot of write lock contention. And it's also not great to have duplicate fee accounts in each program. If you need to update them for some reason, you have to update multiple programs. So we've abstracted them out into a single program, which is our fees program. And we've also created a fee shard account, which is, say there's 256 fee accounts that are PDAs owned by this program, but they are zero data accounts. So they're still owned by the system program, what some people call ghost PDAs. This has the benefit of you don't have to store states, you don't have to do data checks on them, you don't have to pay the rent for data, and you don't have to do manual Lamport math when moving the funds around. You can call system program transfer as you would with any wallet, and that's a little bit nicer for logging purposes. So I'm going to show you what this looks like in a calling program. So, for example, in AMM, we have our buy NFT handler and some shared accounts here. And here we have a fee vault. So it's derived from the seed's fee vault and a shard number. And it's owned by the TFEE program. So the shard number is just the last byte of whatever particular state account is in the program. So on AMM, it's a pool. On Marketplace, it's either a bid state or a list state. And so this little macro just takes the pool, gets the key, takes the last byte and converts it so that it can be used as a seed. So this does write lock to a specific pool. You can't do multiple pool trades at the same time, but you could in anyways because state accounts are mutable because they have to be updated for each trade. So we haven't lost anything by using a state account, but we have gained quite a bit of parallelization because if you assume that state account pub key distributions are effectively random, then we're just getting a random last byte, and we should have a fairly nice distribution and should be able to parallelize pretty nicely. So that's the idea here. And then for state, there's not much here. We have a dummy fee vault struct so that it shows up in the Anchor IDL, and we can auto-generate some helper functions in the clients for it. We have a fee seeds struct, which just makes it easier to pass in the fee seeds when collecting. We have a hard-coded Tensor Protocol Foundation treasury account so that the collect instruction is permissionless, but it can only send to the actual Tensor Foundation treasury. So the process collect takes in an array of fee seeds and the treasury account, and then a bunch of remaining accounts, which are the fee accounts itself. And it just will take the fee seeds, and it assumes that you pass in the remaining accounts in the same order, does the derivation and checks, then it collects fees from these shard accounts, transfers them to the treasury, and it just makes sure to leave the minimum rent for each account so that they're fully funded. So that's it. It's a very simple program for sharding fees, collecting fees in a permissionless manner. This is an overview of the Tensor Foundation Marketplace program. So this Foundation version of the program is a little bit different than the tcomp version that's currently deployed on mainnet. The current version supports listings for CNFTs and MPL core assets. It does not support bids, and it does not support additional standards. The Foundation version has moved over the bid and listing features from other assets into Marketplace so that the new Marketplace program is the one place for all bids and listings on assets of all supported standards. So here you can see the 5 different standards that are currently supported. Compressed are Metaplex CNFTs. Legacy are the original Metaplex NFTs, as well as programmable NFTs, PNFTs. Then there's the Metaplex Core standard, which is their new single asset NFT assets standard. Then there's Token 2022, which is currently just supports the LibrePlex NFT Token 2022 standard, which uses transfer hooks to enforce royalties, but potentially other Token 2022 standards could be supported if they follow the same approach. And then finally, there's WNS, which is also a Token 2022 standard, but uses a different method for royalty enforcements, so is handled differently. First, we'll take a look at the state accounts. There's 2 main state accounts here. List state, which of course represents a listing. This is for a specific asset, so it encodes a specific asset ID as part of the PDA seeds. There's an owner of the listing. The amount is the price desired for the asset, and the currency is which currency to pay that in. The default pub key is for Solana, and then SPL tokens are also supported. There's an expiration date after which the list state can be closed permissionlessly. A private taker allows a listing to be made for a specific owner, so you can sell to a specific person by creating a private listing. Maker broker is so that Devs who are integrating into Tensor Protocol can get a split of the fees by putting their maker broker address. Rent payer is the original rent payer who will receive the rent back when the list state is closed. Cosigner is a secondary signer that can be optionally set up to give more permission control over listings. Then there's the bid state, which represents a bid. This has two possible targets. It can be an asset ID or a whitelist, and then the target ID is the actual value of the target. So if you specify an asset ID, you're creating a bid for a specific asset, and only that asset can be sold into the bid. If you do it for a whitelist, then any item that's a valid member of the whitelist can be sold into the bid. So this allows creating effectively offers on specific assets or collection offers. Quantity is how many of the items you wish to purchase if it's against a collection. Filled quantity is how many have been purchased. Again, we have price and a currency, expiration date, private taker, maker broker, and whether or not to use shared escrow liquidity. So you can attach a bid to an escrow account, and the bid will pull funds from there when making NFT purchases. And the cosigner and the rent payer are the same as on list state. So each standard has the same handlers. It has two buys, one for SOL, one for SPL. It has a closed expired listing, which allows permissionlessly closing listings that have expired. There's a delist, which is closing a listing that has not expired, so only the owner can call this. Listing, which creates a listing. Take bid, which sells an asset into an existing bid and closes the bid. To actually create bids, it's a common instruction that's not specific to any standard, since it doesn't do any transfers or validation of the assets itself. And there's some take bid common logic as well. You'll also note that this one has a no-op, similar to AMM, which is a self-CPI instruction used for logging. So when doing a trade like take bid or buy, the program will call into itself, emitting logging data as an event in the instruction data, so that it's logged to the ledger and is easily parsed from the ledger state without worrying about logging cutoff. That happens when validators truncate logs, the traditional logs via message macro. So this is the same approach used in AMM, if you've seen that video overview. Then a little note here on SPL instructions. These are separate from the SOL instructions because of the additional accounts required. So for token-based accounts like Legacy, there's a bunch of additional accounts because any account that would normally handle SOL now has to have a currency token account. This must match the actual currency passed in, which may be different than the token program used by the asset itself. So if we go down here, there will be two different token programs. Token program, this is for the asset, and currency token program, this is for the SPL token. These could be the same or they could be different. It just depends on what SPL token is being used and what asset is being used. Close expired listing. We discussed that this is permissionless. Once the listing is expired, anyone can call, and as long as they pass in the correct rent destination account so that the funds are returned to the owner, the listing can be closed. This is similar to the close expired bid, which operates in the same manner. So that's basically it. You can create bids either for a specific asset or for a collection defined by a whitelist. You can list specific assets. You can buy those listings with SOL if they're specified in SOL. You can buy those listings with SPL tokens if that's what they were specified when they were created. SPL support is not currently set up for bids, only for listings and buys. And bids can be created and taken with TakeBid. This is an overview of the Tensor Foundation AMM program. So the AMM program is a liquidity program, automated market maker for NFTs. So it allows users to create pools that can either buy or sell NFTs based on a whitelist defining a collection. So it's a way to create a market-making style AMM pool for NFTs and NFT assets. We'll take a look first at the state. The main state account is the pool. So this defines a pool. It has a whitelist, which determines which NFTs can be deposited or sold into the pool. It has a version, the PDA bump, an owner chosen identifier, some timestamps, the owner, who's the update authority, and the nominal owner of any NFTs escrowed in the pool. Rent payer, currency. This is for future support of SPL token purchases, but is not currently supported. And an amount, this tracks either the native SOL or currency held in the pool. Price offset, which determines the next price of the pool based on the number of NFTs bought or sold, the number of NFTs currently held, some various stats for the pool, historical stats, whether or not it has a shared escrow account attached to it, if it requires a cosigner, a secondary signer to sign off on pool actions, maker broker, max taker cell count. This is used to limit how many trade executions a pool can execute against a shared escrow. And a pool config that determines the type of pool it is, the curve, etc. So we'll look at that. Pools have three types. They can be a token pool, an NFT pool, or a trade pool. The first two types are single-sided pools. So a token pool stores SOL. In the future, potentially any SPL token, and it can purchase NFTs using its stored token. An NFT pool is a single-sided pool that holds NFTs and sells them to users. And a trade pool is a double-sided pool that can either buy or sell NFTs depending on if it has NFTs escrowed or if it has SOL or other token escrowed. The curve type determines the shape of the curve that governs the pool prices. Two types are supported, linear and exponential. The starting price is where the point on the curve starts. The delta determines each step on the curve. Compound fees, compound fees, determine whether fees stay in the pool to be compounded or if they get distributed to the owner. And the fee basis points is the basis points for the fee, which the fee is basically the market maker fee. It's a way to reward market makers of trade pools. So market makers who provide double-sided liquidity get rewarded with an additional fee that they specify when they create the pool. And then the pool has some various utility functions for determining price, calculations. Probably a good place to look at for auditing or shift price, calculate price, because it does the math for the different pool types. And should be doing check math everywhere with precise numbers, etc. All right, we have a second state account, which is the NFT deposit receipt. So this is created whenever an NFT is deposited into a pool to be escrowed by the pool. So whether that's the owner calling NFT deposit or a user selling an NFT into the pool, we recreate a receipt that is uniquely tied to both the mint, so the NFT asset, and the pool. And this validates that the NFT was put into the pool via the program's logic itself and not just transferred externally. So otherwise, you could potentially transfer an NFT to a pool and bypass the whitelist for it. So we talked about all of that. The whitelist itself is used to validate what NFTs can be deposited. Once they're deposited, they have an NFT receipt created for them. This is the same thing as the NFT deposit receipt, but it is called the asset deposit receipt because we want to support non-mint accounts. And basically, it's sort of a dummy account that lets us generate some client resolvers and utility functions automatically by using asset as the field instead of mint. So it's not really used on chain. It's just used for client generation purposes. So let's look at the pool functions first. You have create pool. It's pretty straightforward, explanatory. You pass in pool config, whether or not it's got a cosigner, maker broker, max taker cell count, these things, and the pool config. And it lets you pass in a currency, but currently we are only supporting Sol. So I think we're checking. Yes, we're just assigning the currency to the public key default, which is the native Sol currency, mint, effectively. So this is just future looking for supporting SPL tokens in the future. So we have that. Sets up a pool with an authority. We have close pool, which the owner must sign to shut down a pool. And we have we deliver the rent back to the original rent payer, which is stored on the pool, and we enforce that the pool can't be holding any NFTs, so you don't maroon NFTs that were deposited. They must be withdrawn or sold. Then we have deposit Sol, which is the proper way to deposit Sol into the pool. If you transfer Sol directly outside of the program, it will be not counted in the pool's amount. And so the logic dictates that we update this amount field. We use this for calculations on how much Sol is available as like a security thing. We don't want people to be able to reopen dormant pools by depositing Sol into it in order to sell into it when the owner's not expecting that to happen. We have closing the pool, which must be done by the owner, and funds go back to the original rent payer. And again, NFTs held. And then we have a variant of this, which is a close expired pool, which is permissionless. So the owner must be passed in for seeds derivation, but anybody can close an expired pool as long as it's expired and it's not holding any NFTs, and they pass in the correct rent payer so that the funds go back to the original owner. You can close an expired pool. Then we have edit pool, which lets the owner update some pool config values. We make sure the config values are valid, and then we set them. And then there's a withdraw Sol, which just takes liquidity out of the pool and must be done by the owner. And then we have a single admin instruction, which is the TAM no op. This is used for logging. So this is just a self CPI call. It's the pool program CPIing into itself, using its state account to validate that it's allowed to do this, and then using the instruction data as a logging mechanism. So this is a familiar pattern probably to most of you. This is the way that CNFTs work, is they do a CPI to another program and use the instruction data to log the CNFT data, so that's present in the Solana ledger. And Anchor has a macro to do this for self CPI logging to get around the normal logs 10K cutoff that validators will do. So that's what this is for. We do our own instead of using the Anchor macro because we want to use an existing state account rather than creating a custom state account for logging. Just saves one account. When we have a lot of accounts, it's nice to minimize those. All right, so then we have 3 different standards currently supported on this program. Legacy, which is Metaplex's legacy NFTs and also programmable NFTs, known as PNFTs. We have Metaplex Core, which is their new single asset core standard. And then we also support Token 2022 NFTs built around transfer hooks. Currently, this only supports the LibrePlex Token 2022 standard, but could support other ones similar in the future. But this does not support WNS, which uses a different approach and needs more custom work. So each of these standards has a buy NFT, deposit NFT, sell NFT token pool, sell NFT trade pool, and withdraw NFT. So you'll see that these handlers are duplicated. And the reason we have to have separate handlers for each standard is each standard is a little bit different on how the assets are transferred, how the assets are validated. And so we split them up for ease of use, but we do have a shared account struct I'll show you in a minute. The other thing to note is that buy NFT handles both pool types, NFT and trade, whereas for sells, we have separate handlers to handle token pools and trade pools because it makes logic and things cleaner. So let's take a look at buy NFT, and I'll show you this trade account setup. So what we've done is all trade instructions share a trade shared account struct. So trade instructions are buys and sells. And then all transfers, which are deposits and withdraws, have a shared transfer struct. And so these are shared across standards. So if we go and look at a different standard, you'll see we have the same trade shared account. So we've abstracted out here all of the accounts specific to trades, but not specific to standards. And so this allows us to clean up our constraints and only have to check constraints in one place. And we can do some validation functions all on this struct and not have to repeat this logic for every handler and every standard. We also have a shared struct for each standard itself. So this is a Metaplex legacy. You'll see all of the accounts specific to the legacy, all the token records, authorization rules, program, token metadata program, etc. Then we have the same thing here. We have an MPL core shared, and we have a token 2022 shared. So those are the 2 shared structs, and then we'll have any additional ones that are necessary for each standard here. Then the handlers, you'll see, follow a very similar pattern where they run some pre-processed checks, which validates anything specific to the handler. So in this case, we have a buy validation, and then we validate that we've received a legitimate MPLX asset. And so this is a trait, validate asset, that we implement for each standard type, which makes for nice, clean, reusable code, but it lets us do specific validations on each standard type since they're all a little bit different. So we run this pre-process checks first. Now we have validated the handler and we've validated that we have a legitimate asset here, and this is a generic AMM asset, which just represents an asset of one of these standards as perceived by the AMM program, basically. Let's see if we can actually look at this. We just have an address for the asset. We're not calling this a mint because it could be a mint-based NFT or it could be an asset NFT. So it's just the generic pub key that represents the asset. It could be a collection. We have some creators and other things we get from the metadata so that we can do our fees and royalty calculations. So we have our assets, we get some other accounts we need, we do some calculations of fees, then we basically transfer. Since this is the pool buying an NFT, we're transferring the NFT into the pool. If it's a token-based standard, we close any unneeded token accounts. We do our buyer fee calculations. Since we're selling an NFT out of the pool here, a user is buying from the pool, we can close the NFT receipt and reclaim the rent for that. Update pool accounting. And then if it's a single-sided pool and there's either no more NFTs left to sell or not enough SOL left to buy an NFT, we will auto-close the pool if possible. And so this is the basic trade flow. You'll see this here. Again, in sell, pre-process checks, calculate fees, do the transfer. In this case, the transfer goes the other way. The user is transferring into the pool. For PNFTs, we have to do this weird double transfer where we transfer to an escrow account first and then to the owner. Because a token pool does not escrow the assets. Instead, they go straight through to the owner because the token pool is single-sided, so we don't store any assets on the pool itself. And Metaplex PNFTs have a weird check that they need in order to enforce royalties that requires us to do this two-stage transfer. That's the simple explanation. And then the rest of the flow, close token accounts, update accounting, pay fees, try to auto-close the pool. You'll see the trade is similar, but because the pool escrows the asset, after we do our checks and fee calculations, we can just do one transfer into the pool, have less token accounts to clean up, but similar stuff. And you'll see here that because an NFT is being escrowed by the pool and deposited in, we are creating an NFT deposit receipt. The transfers are similar in that we have this pre-process checks that does any validation necessary, but we have a little bit less logic to do because we're not paying fees because it's not a trade. So it's just the transfer, cleanup, pool update, create or delete NFT deposit receipt. And all of the standards follow this flow, so they should be fairly easy to follow. It's just the difference of how the NFT asset is being transferred. Usually is the main difference here. And this one does not have a token account to close, but we do try to close the NFT receipt account. I think that's the main thing. Let me show you some. So the token 2022 has a little bit of extra stuff. We have to get the creator accounts from the transfer and use those in the fees. But other than that, it's the same flow. So the shared accounts file here has all of these shared accounts and all of the shared trade and transfer validations and fee paying and calculate fees. So this should make it easier to audit because it's very dried up. Instead of repeating this code across multiple instructions per standard and 3 different standards. We've abstracted it away as much as possible. And so it should be easier to validate because you can validate the transfer shared struct once, and that's used in every transfer on each standard. So I think that's the main thing to cover here. Yep, it's a AMM program that has single-sided and double-sided pools. Uses NFT receipts to validate assets that were deposited in. Uses a whitelist to validate which assets are allowed to be sold or deposited into the pool. It has an owner which receives the funds from buys and sells, or receives the assets from token pool sells. The pool itself will escrow NFTs and SOL, depending on the pool type. And that is basically it.